Hello, welcome everyone today. Thank you for your patience. I'm Sarah Nasruddin from AVL Hungary, and I will be the technical moderator for today's online event. We are speaking from Zalazon Proving Ground from the city Zalaegerszeg in west of Hungary. Now I would like to share some technical information about the webinar. Today's webinar will be about 45-50 minutes long. If you have any question regarding the topic or the presentation, or if you have any technical problem or issue, please type it to the chat. After the presentation, the presenter will answer your questions. Before we start, I would like to give the word to the sales director of the AVL Zalazon Proving Ground, Mr. Miklos Kovács.
Hello everyone, this is Miklos Kovács speaking. I'm the sales director of Sarasat, the AVL Zalazon Proving Ground. This is my utmost pleasure to welcome you at this event, which is, we believe, the first of a series where we are promoting what we think we are best at, and that is the testing and validation of autonomous and electric vehicles. I don't want to waste your time, and I hand over to Marci, my colleague, who will explain you what and how we do here. Thank you very much and enjoy the event, and don't spare your questions with us.
Okay, well, welcome everyone. My name is Pataki. Thank you for the opportunities to participate on this event, this webinar organized by AVL. As I said, my name is Pataki. I'm working here as a test engineer. Previously, I was working here as a project support engineer, but currently I'm working on ADAS testing activities and other related stuffs. I will share my presentation with you. Please, a minute. Okay. I would ask feedback. Do you see my presentation or not? Can you someone write in the chat?
I don't see, Marci.
Okay. And now?
Yes.
Okay. So, okay, here you can see the content of this webinar. This is the backbone, what I want to share with you. The topic itself is about ADAS testing. That's on the developer side, more based on testing experiences. I would emphasize that I don't want to, or I won't tell you the best practices. I would rather summarize the task and the processes we have faced until now. I tried to sort all of the aspects what we need to be considered during ADAS testing, from the standard itself and its requirements through the devices and track modules that we have to use for the testing all the way to the evaluation. Finally, I will look at the future test, and I will also briefly present a new testing approach that we are developing here at Zalazon, but I wouldn't spend a lot of time with this topic because, my opinion, it's a topic should have an own webinar session. Yeah, and I will touch some challenges what we have faced during our activities. I know the definition of ADAS is clear for everyone. These systems are those functions which could improve our road safety, or it can enhance the comfort of the driving, relying on sensors such as typically radar, cameras, LiDAR, or even ultrasonic sensors. Although today they can also help the driver by relying on information extracted from HD map. This type of functions typically use the localization unit, high accuracy GPS. I think because of the importance of safe mobility, the safety ADAS functions will be mandatory. Firstly, such as automated emergency brake system, or I could mention forward collision warning as well. But parallel with these safety functions, there is also a growing demand for convenience, so the comfortable features, just like adaptive cruise control, or I could mention the park assist system as well. On this slide, I would summarize our 5-level approach to test and validate ADAS functions or in the future car. Generally, the examination process starts with simulation activities. The advantage of this simulation is to observe the basic operation of a function already in a development phase. After a well-prepared simulation environment, the functions can be tested much more faster than in the reality without significant resource usage. In most cases, the simulation could be enough to investigate the basic operation logic and algorithm. The currently available simulation tools are able not only to calculate the expected results based on a model, but it can visualize supposed events. There are more simulation tool developer companies providing also hardware modules besides their software, so that the engineers can investigate a car, for instance, in a test bench within a laboratory environment. One of the most significant advantages of the laboratory evaluation is that engineers can attach real hardware components to the end of the chain, and through this we can produce real outputs based on feeding input data. It's not uncommon today to test the entire vehicle under laboratory conditions by moving the vehicle itself, or how could I say, the powertrain itself. What's more, today there are now labs where you can test your vehicle sensors in a chamber, or for example in a room. If you just put a vehicle and you can stimulate a different simulated feeded signs. These signs could be, for instance, the radar signs, or you can project around the car with videos and which conform for the reality. Based on the level of the integrity of the system intended to be investigated, can be the following. For example, we can speak about software in the loop, hardware in the loop, or vehicle in the loop. In most cases, the flexibility and the effectiveness provided by simulation is not enough because the complexity of the reality, which affects the behavior of the entire car from many different aspects, like perception or coming from real disturbances or dynamic aspects and so on. When a car is intended for serial production, we have to investigate the car in the reality, but in safe environment, close away from the public road. And in order to avoid the possible malfunction, which can, of course, cause any dangerous situation in real traffic. So for this purpose, more and more test tracks built in the last 50 years, some of them are upgraded for investigation of automated vehicle functions, The last few years, most proving grounds struggled to meet these needs, and some of them started to build new urban environments, or for example, junctions, intersections, and so on, which were generated by the development of this, driving and automated cars. When the development of the ADAS function reached its final phase and prove its reliability with a closed test track, they should be investigated in a public road where much less predictable influence factor can occur. It can increase the number of the scenarios, and we can divide the public road testing into two subgroups. The first, where the car is in a tested limited environment road section, where some kind of extra regulations support the testing in order to minimize the risk of the vehicles which are tested in this environment. And there is another environment when it's for free to test in real traffic without any limitation. But this presentation is focusing on the testing on a closed proving ground, wherein that the ADAS test protocols are used by automotive industry. The ADAS test protocols are defined in the last few years are very similar. In most cases, these test procedures belonging to different ADAS functions is not mandatory. There are only some UN ECE regulation concerning to typically AEB or LDW functions, but mainly these are compulsory only for the trucks, but the AEB, so automated emergency braking system regulation related to passenger vehicles, is already mandatory. Until now, there are more institutes and organizations which develop their own test protocols and procedure to investigate the ADAS function. The purpose of these processes is to support the car buyers evaluating the safety rates of these vehicles before they intend to purchase the car. The most common organizations are the UN ECE within Europe and the IHS or NHTSA in America. They all belong to new car assessment program. As they provide a general picture about the passive and active safety performance of the investigated car, these results have significant effect on the market sales. That's why the most car maker and the tier 1 suppliers try to fulfill these requirements and these tests, which are defined by this organization. Besides that, there are more standards organizations try to standardize these test procedures supplemented by new scenarios. These organizations are typically the ISO, but SAE has also recommendation to test some of these ADAS function. Even if the test procedure are published and used in a word are very simple, if we take in consideration all of the combination of the factors can affect the vehicle behavior. But the Euro NCAP protocols rely on the survey of the car maker. So it's some kind of homologated procedure based on the industrial inputs. That's why they involve the relevant stakeholders to determine the basic scenarios. The Euro NCAP created different working groups focusing on the functions involved in industrial partners. On this slide, you can see the content of a typical Euro NCAP test protocol, which is very similar in case of automated emergency braking tests, or the lane support system protocol has the almost the same backbone. Each test protocol started with a short introduction where drew up the function to be tested and the relevancy of the investigated situation. In detail, the reference points of the actors within a scenario and the coordinate system convention. It defines which variable should be measured and the frequency and the filtering of the data acquisition. The document also describes the conditions concerning weather and the requirement of the test sites. I mean, first of all, the surface itself, the road marking or the inclination of the surface. Last but not least, it illustrates the scenario with figures, and they give an exact dynamic parameter should be fulfilled under test execution. On this slide, I would summarize all of the test equipment is needed for ADAS tests, not only for the standards, but generally. We can divide them into more groups. there are dummies which represent the traffic actors in a dangerous situation. They have to be similar compared to the real actors in physical properties. On the market, more type and dummies are available. There are child, adult, pedestrian dummies. There is bicyclist and motorcyclist dummies, or even scooter, as far as I know. More type of passenger cars is also available in the market, and I've already seen maybe wide dummies as well. In order to move them at the required speed and acceleration, deceleration on the path, which are defined in scenarios, a programmable self-driven platform is needed. For smaller dummies, just like this group is the vulnerable road user, including the pedestrian, bicyclist, and motorcyclist dummies, or the wide dummy as well, can use the bed-driven system as a propulsion system, but appropriate synchronization with need to accurate position of the beauty. So we have to mount the automotive industrial GNSS system with IMU and RTK corrections supported the GPS functionality. But we can also use a much more simpler bed-driven system, not only for this self-propelled or self-driven platform. The RTK correction can be received from the local DGPS base station, or we can subscribe for NCAP service as well. So we have all the independent actors, but we need to synchronize them so that we have to apply the suitable software tool to operate them. All of these propulsion systems, supplier company have their own trajectory planner and synchronization software too, but for the communication, we need to ensure the communication network among the participants of the scenario. In most cases, these suppliers provided their own mesh network, and we have to attach the radio antennas to the actors to transmit their position or speed data through the synchronization tool. All of these items are needed to operate a complex scenario with multiple actors. The simple scenarios when you just intend to set up only a crossing scenario or longitudinal scenario with a bed-driven system, you can apply a simple light gate trigger system, so you don't need to full synchronization mode. But the reliability is much lower, and then continuously controlled and synchronized system is much more useful and effective. The protocol doesn't define the exact propulsion system, as I already mentioned. For these devices should be used these protocols, but they define basic requirements in order to decrease the effects came from the equipment, I mean the false sensor reflection. By the way, there are solutions which are self-propelled platform with low profile, as already mentioned, which are able to withstand even that when a real passenger car or even a truck drives through them. Most of the self-propelled platforms are able to drive with more than 80 kph speed by maintaining even 3 centimeter accuracy with help of built-in localization units. Maybe you could watch the video about how setup of this foam panel target before testing. The base of this foam panels is the moving platform itself. The operator has to build up its foam panels. The foam panels are connected by backrow fasteners. Finally, they have to attach the covering shell panels, which has to appropriate visual design. A smaller self-driven platform is to carry the VRU dummies, like the adult child pedestrian dummies or the bicyclist, typically for AB test protocols, but currently only bed-driven system is approved by UN ECE organization. As far as I know, maybe there are solutions with official solution with bed-driven system, not bed-driven system, but self-propelled platform with extended arm. But mostly this bed-driven system is approved and used by UN ECE official labs. This kind of pedestrian dummy is manufactured from different type of foam body while being able to simulate human behavior with their foot movements. During the development of these devices, the engineers took care of the shielding, the disturbing reflective mechanical elements, which can absorb the invalid radar reflection. The required radar and infrared reflection is defined in the appendix or the technical bulletin document published by your NCAP. And on the bottom, you could see a video about how does the belt-driven system operate. Typically, there is a driving unit with electric motor, and on the one side and on the other side, there is another unit responsible for the tensioning and returning of the belt. This is an endless belt system. So the alternate movement of the pedestrian dummy is suitable to perform crossing scenario from lateral direction. And with smaller upgrade, there is a winding unit. It is convertible for longitudinal scenario as well. That was the devices that we can use, and here I listed some of metrics that you have to measure during the test, and data filtering requirements and frequency that you should be consider. Okay. These some slides will show you how many different scenarios will appear within your NCAP and other further organization. This section will be made a little slow or exciting, I'm sorry. Within AB car-to-car protocol, 3 different radar and situation are detailed with an additional turning situation. The target device simulates oncoming traffic across the VUT's turning path. The target as a GVT, so global vehicle target. We differentiate 3 basic radar and press situations according to the behavior of the target vehicle. There is a static scenario where the target is a standalone object in the path of the VUT, and the VUT has to approach it with different speed, typically from a speed range between 20 kph up to 80 kph step by step. In the second scenario, we use the target moving with constant 20 kph speed, where the collision situation depends on the relative speed between the VUT and the target. The VUT is tested in a range from speed from 30 kph to 80 kph. The third situation, the braking scenario, when we repeat 4 combinations, depends on the deceleration of the GVT or it depends on the headway. So the distance between the GVT and the VUT, the headway could be 12 meter or 40 meter. The braking intensity change selectable is one of them, 2 meter square secondum and 6 meter per square secondum. And we have to combine it into 4 base cases. In the turning situation, the VUT examined only 3 very similar turning paths. In the turning section of the path, the curve section is built up from different clotoids. Different test feeds belong to different type of curves. The upcoming test protocols includes already scenarios with motorcyclists as well. These are similar to the car-to-car scenarios. Here will be also rear and crash situation, but besides these tailgating scenarios, there will be extra overtaking and oncoming situations, such as in the well-known lane support system test, but I will mention it later on. I mean the lane support system test. The automated emergency braking situation, where we test the car in interaction with pedestrian, can happen from lateral direction or longitudinal direction. We can separate crossing scenarios into near side scenarios and far side scenarios. Near side scenarios, of course, where the rear dummy comes from the right side, and in case of far side scenario, the dummy comes from the left hand side. In the longitudinal scenarios, the VUT approaches the target from behind. In some situation, the protocol investigates the system in further runs with different overlaps. Overlaps means the distance of the shifting between the center line of the VUT compared to the GVT center line, and we are offset to each other. In the longitudinal scenarios, the VUT And there are some scenarios where the test engineer have to park or place some static disturbance car in order to limit the visibility of the vehicle, or in other words, I can explain it. You can limit the field of view of the sensor. Of course, these cars hide the device coming from the slide, challenging the VUT's ADAS function. Within the UN ECE various protocols, there are two basic scenarios in dark conditions, so in the night. One in one case, the traffic you can use traffic illumination, and in the other case, you have to execute it without any public lighting. Here you can see the bicyclist scenarios, very similar to the pedestrian scenarios. There are longitudinal and also crossing situation. In case of both sides, we have to make challenge for the sensors with obstruction cars, and there is an extra door opening scenario that will be only rated from 2023, where VUT has to prevent a door opening before the bicyclist would hit the door. So in this situation, there is again a covering disturbance car behind the VUT, and the disturbance car is in a static, and the VUT also tested in a static position. The current two turning pedestrian scenarios will be extended to additional scenarios. The original two scenarios are released, as far as I know, in the last year, and the difference will be only the direction of the pedestrian dummy. In these new scenarios, the pedestrian will move into the same direction compared to the previous published scenarios, where they come only from the opposite direction. So that is the difference. And the two type of the reverse AB scenarios already known in the previous release, the protocol. There are static and moving situation. The static one is tested in 3 different positions. The UN ECE defines the test execution parameters in different tables, and it assigns them to a unique codes, which can shortly describe and identify the scenarios. UN ECE investigates each scenarios under more speed combination or at more different VUT speed step. Maybe I already mentioned it. On this slide, I would summarize you that scenarios which are conducted under investigation of different functions related to typical lane support system. Within the lane support system, the UN ECE defines 3 main functions. These are the emergency lane keeping system, the lane keeping assist system, and the lane departure warning system. There are 10 different layouts for these tests. In most cases, the differences are the number and the type of the road marking or the presence of the road edge. But there are very similar scenarios where this distinction or difference is only the trajectory of the VUT. For instance, in one case, the VUT approaches the center line from the right side, and in the other case, the VUT has to execute this maneuver from the left side. The speed of the VUT in most cases, especially ELK road edge scenarios or ELK A and the LDW scenarios at 72 km/h speed. The definition of the path which describes the trajectory of the VUT depends on more parameters. 2 of these 10 scenarios involves an additional participant, which is typically the GVT. Depending on the maneuver of the GVT, we can differentiate 2 scenarios. One is the oncoming situation, where the VUT follows its path towards the center line, and the GVT comes in the oncoming lane at speed of 72 again. In the other scenarios, the speeds are 72 again and 80 kph speed, where the GVT coming from the behind of the VUT in the adjacent lane, simulating an overtaking or a blind spot situation on the left side. As I mentioned, the organizations like ISO and SAE also released their standards regarding ADAS functions. The ISO 15622 is investigated ACC functionality in 4 different scenarios. The ISO 15623 is about FCW tests, which are very similar to UN ECE ISO ACC protocol, but these ISO procedures are not so exactly So they don't define always the magnitude of the acceleration, deceleration of the participants. So they, how can I say, they can have the freedom for the engineers to choose these parameters. ADAS standards for pedestrian bicyclist situation as well. They are detailed in separated protocols. The ISO 19 to 37 standards, two crossing pedestrian scenario are defined. One of them is running during a day condition, and the other one is under night condition with illumination. The coming pedestrian from the lateral direction has to maintain 5 kph speed, and while the VUT has to be driven with 30 kph speed. There is a simple pass criteria, and it's not use relative speed crash compared to the Euro NCAP evaluation. Longitudinal crossing bicyclist scenarios defined in the ISO 22078 standard. This is a standard related to not only passenger car, but also the heavy-duty vehicle. In the longitudinal scenarios, the bicyclist target has to be towed at 4 as far as I know, 4 meters per second speed, while the VUT is coming towards the collision point, 11 meters per second or something like that. In the ISO 22839 standard, the forward collision warning mitigation system are evaluated under the same situation, just like in the ISO 5623, which is focused on the warning system mainly. The American IIHS also protocols for the car-to-car and the car-to-pedestrian situation, but much simpler compared to the Euro NCAP. Muse project was a preliminary project in 2018 before Euro NCAP released the new year protocols. Compared to Muse, the new Euro NCAP increased the PTW targets from 15 to 60 and 80 kph depending on the situation. In the simple crossing scenarios, was this changing from the 50 to 60, and lane support system situation to the oncoming and overtaking scenarios, the changing was from 50 to 80 kph. Okay, the engineers often have to consider the location of an ADAS test, mainly if the sites are occupied by another test session. The most challenges come from the space demand of the test or the special lane marking request. By the way, the Euro NCAP defines exactly the lane and the road markings, but the customers have often unique needs. So the service team have to adapt somehow to them, and we have to mark precisely or blue or place the sticky road markings according to the customer's need. The evaluation as a final step of ADAS testing typically has 2 roles. On the other hand, we have to evaluate the performance of the vehicle according to different metrics. For instance, in the case of rear-end crash situation or test or the vulnerable road user AEB test, we have to measure the impact speed because it is counted in the rating in function of test speed. But for example, for the LSS test, we have to log the time of the intervention of the lane keeping function or the time of the warning generated by an LDW system. So this is the lane departure warning system. On the other hand, our further goal is to keep the test runs repeatable. Furthermore, thereby these tests might be objective. In order to measure and ensure it, we have to use driving robots and localization units. Detail level of the evaluation usually depends on the customer's need. Of course, if they need a homologation level test results, we have to log the data, check the compliances with the described or predefined tolerances, but sometimes they even ask to score the test run for the full rating. But the experience shows that most of the test requests come in the development phase, and they don't need they just need only log data in an exported format what they need. Sometimes we don't have to worry about keeping the strict trajectories and occasionally human driver VUT is enough for the test, and rarely it can occur that the customer required to deviate intentionally from the predefined or standardized parameters. In those cases, when the customer asks the full evaluation report, then there are tools which are able to do it automatically. It doesn't mean only to rate according to the measured result, but it can indicate or assign it somehow to the engineer that actual run meets all of these specifications, or maybe doesn't. Most of these test devices supplier have an own tool for it, but third-party companies also provide a similar solution. For example, AVL Smart ADAS Analyzer is a tool which can provide a comprehensive solution, which not only evaluates or plots only these graphs, but it also shows the guidance for the test engineers. The third-party tools advantage is that they try to be compatible with other test tools manufacturers. AVL has experience with, as far as I know, the proactive systems, the AB Dynamics, and also humanistics tools. Here at Zalazon, currently we are using the AB Dynamics own post-processor tool, which is a built-in solution in this test environment. And of course, there are available general tools to build up your own evaluation script, even also a report generator. You can see it on the right side on this slide. This could be a MATLAB or NI tool or a Skylab and so on. So there are more opportunities for this purpose. Okay, challenges we have to face every day is to execute the test precisely. This is the biggest challenge. In order to fulfill this basic but not easy requirement, we have to use RTK correction, as already mentioned, for our robots and platforms, which controls the players within a scenario. The accuracy of the test execution depends on the GNSS status. It's often influenced by the weather conditions, according to our opinion. Sometimes easily accessible and well-made in the accuracy, but sometimes we have to spend more time to stabilize it. The robots use as an input, so the success of the war scenario depends on this. The weather can influence not only the localization, but also the target itself. For example, when the wind can push or upset these targets, it can cause an emergency stop, because when the wind push or move the target, the platform or this robotized devices feels as if it would be under external influence, just like in a press situation, so it activates the emergency brake. There are more devices which is not waterproof totally, so it can also result some limitation. Other complicated tasks when parallelly more customers need ADAS tests, and this can result that we cannot manage the test on the usual pace, so we have to adapt another site. I mean, other test track module where the condition is not always perfect. That's why the preparation can take more time. We have to do a good prediction and estimation for the time demand, and we also need to know the alternative sequence for successive tests. For example, if a device fails or not available for longer time, we need to care about their replacement. We can spare time if we settle in advance more scenarios parallelly in the same track module, if it's possible. So after an unsuccessful run of the VUT can perform a further other run in the adjacent same site, so he can perform another type of test until while this test equipment, for example, in the previous scenarios, the platform has to be returned on its return path to the start position. So we can spare time if we use this type of, how can I say, look ahead strategies. Okay, and the challenges can be on a long term, not only the short term, but we face the day by day. This slide summarizes these long term issues. With the rapid development of ADAS, more and more challenges pop up. Over time, the operational range of the ADAS functions increases, and the test execution company has to prove the adequacy of or the compliance of their operation. For this, they need new and more advanced tools which can operate wider range, for instance, higher speed, higher acceleration, and so on. It requires further investment, and since these devices are very expensive, the companies has to consider it from utilization or the payoff aspects. The mobility transformation also brings a cooperative vehicle control usage and more advanced function. When this current use system, they attach communication layer or functions. For instance, this type of ADAS function can be a connected adaptive cruise control. The further important issue is the simulation. A lot of companies started to working on their own concept in order to supplement the real-world testing with these simulation solutions. There are aspiration and working groups who started to elaborate standardized description of the scenarios, but currently the standards and the regulation only touch this question just carefully for now. This is the roadmap, which is also available on the UN NCAP side, and I suppose that more and more new protocols will be released soon. The latest protocols for VRU, AEB, and LSS tests, and LSS tests for car-to-car, but I'm not sure. But the VRU is sure. Interaction just appeared recently, maybe last June, but they will take effect or will be counted into the rating only from 2023. The car manufacturers do not only test according to these standards, but they increasingly intend to investigate the performance of the ADAS function in more complex environment where more disturbance and traffic actors appear within a scenario. These complex scenarios requires more devices and their synchronized operation. Most of the test devices providers started to upgrade their system to fulfill these needs. We have experience with Zalazon, as already mentioned, the AB Dynamics and this pool of test tools already able to complete this type of request. So we can perform this type of complex scenarios. At Zalazon, we have two self-driven platforms, two sets of riding robots, what can be installed into passenger vehicles with automated gearbox. Furthermore, we have a drive-by-wire upgraded or controlled Kia, which can be used for these scenarios as a disturbance traffic car or for them as a demonstration car. And in addition, we have a belt-driven system for VRU targets. In addition, we have total 7 localization units. We can control 6 actors robotized and or programmed in the synchronization way. And we can attach one more human driver vehicle if it's needed. This video would demonstrate how can we perform this type of localization, but I have to say sorry, but the video is lagging, so I replaced it with these 4 pictures, and but we will share with you the video links. You can see here there is a situation where the Kia as a demonstration car approached this bicyclist. So the demonstrator car passed by the bicycle, and after that, when it approaches the junction, they have to give a free way for the oncoming GVT global vehicle target. After this intersection situation, the Kia will meet a crossing pedestrian on the picture number 4, and it is a simple crossing scenarios. Yeah, and maybe I skip. There is a disturbance vehicle in the junction, which is only crossing the path of the VUT, and this is a gray Van Wagon, a robotized car. Okay, this scenario is a complex scenario. The difference is only the site, and the scenario itself is another type of scenario, but the complexity is almost the same. We use this pool of devices in our smart city zone in this real urban test environment. We use also the Kia as a demonstrator car. There is a crossing pedestrian situation which is supplemented the braking disturbance GVT. And VUT is robotized Kia, which is a upgraded drive-by-wire car. after a pedestrian interaction, the next situation is a bicyclist interaction when the bicyclist is riding on the bicyclist lane. Compared to the scenario that I presented on the previous slide, which was recorded on our brand new ADAS platform, here is a smart city zone. So we can provide much more complex urban test environments with different lanes, pedestrian crossings, pavements, or sidewalk with curbs. Moreover, the facades representing real buildings and different type of buildings are currently under construction. At the latest, they will be finished by end of this year, hopefully by end of this summer, but yes. And in the meantime, our R&D department started working on our quite new testing approach, which utilized the advantage of the simulation and the real-world testing. They already have practical results, among others, in area of interfacing as a first step between the equipment, the AB dynamics tools, and the simulation tools. The new methodology will be able to handle not only the real but the virtual objects in the same time, even in real time. All of the participants can be controlled and triggered from the simulation with help of real-time feedback. The base of the virtual environment is a centimeter accurate HD map, which is already available about all of Quinif Zalazon test track modules, even for our customers. So if you need, just register, please sign to us, and we will provide you the link in order to download the HD model in different format. So this is our scenario in the loop concept. I wouldn't speak more about the details because I suppose it will have an own webinar session in the future. And yes, that's all what I planned for today. Thank you for your attention. And if you have any question, I try to answer them. Thank you. I would stop sharing the presentation. Okay.
Thank you, Marty. Can you see the questions in the chat?
Maybe I already seen one question, but
I can read it. So the first one is, what is the operational range distance of a platform?
Yes, I can see. And okay, I try to somehow summarize because it's not too easy to answer it. The manufacturer promises a whole-day availability for the large platform. This is the GST, or it's responsible to carry on the global vehicle target, the GVT. Our experience is that it depends on more factors. Again, if you can use with a higher speed and with harsh acceleration without any failures. So in this case, then the battery is completely discharged by end of the day. But in that case, if we have but yes, I have to say that this occasion is a very, very successful day. I mean, it's about 8 hours on one day. We have experienced this AB dynamics tools, but as far as I know, other manufacturers have slightly shorter driver range with a single charge, but they can maybe swap the battery for a fully charged set. Our large platform has a built-in battery, so if we have to charge it, then it's not available for the test. We have a small platform which called as a Launchpad. Has already a swappable battery, just like for other customers' devices, but one set of battery has a shorter drive range compared to the large platform. It's enough about half day long if you can use on 100% availability. But these values are experiences, so it can also depend on the weather conditions. For example, if the temperature is too cold or it's too high, too warm, these numbers can reduce, of course.
Thank you. Marcy, okay, the second question is, are there any requirements, standards for the NCAP test done during the night conditions?
Yeah, there is a bulletin or appendix for these illumination devices. So you have to measure the intensity of the light that you want to apply or use for night testing, the exact position of the pole of this light system is exactly defined with dimensions. So before you would just perform this type of test, you need to measure the intensity of the lighting in a certain predefined position with certain predefined devices. So these devices shall be calibrated, and yes, you have to use currently, as far as I know, 5 pieces of this public light mobile pole. Okay. Next question. So I cannot separate easily the sentence in the chat section. Yeah. Is it possible to make an ADAS test after windscreen replacement?
What kind of preventive settings or functions are robots to operate?
Okay. So for the steering and the pedal robot, we can set some kind of limitation when we home them after the powering on. We can set the limitation under the default means setup menu, but even within a certain test, we can do it again. For example, we can limit the steering velocity, the steering angle, or its acceleration in case of a path following test, but we can do the same for open loop simple steering test as well. Besides that, it's watching constantly the path following error compared to the path intended to follow, and if the deviation is bigger than a certain threshold, it will deactivate the robot. We do not have to worry about the wrong GPS input data because AV Dynamics provided this solution. In case of platforms, also we have almost the same functionality, but these are so-called driverless tools, so we can also set additional geofencing limits and boundaries around or on the test track what we are using for the test. There are further conditions. For instance, if there is a certain long communication dropout between the remote controller, the base of the control, and between the platform. The platform activates its mechanical safety emergency brake. By default, the system do not allow to run a test with this platform without appropriate GNSS accuracy. So it is also a safety feature. Yeah, there is a question about windscreen, the replacement. Currently, we don't have experience, so we are not familiar with this type of test. But and ADAS function calibration for now. But maybe in the future, we will welcome this type of needs or requests. So we are open. If anyone has this type of request, we try to solve or support it, but we don't have experience in this topic. Okay.
I saw some questions about this webinar. So this webinar is recorded and we will share it in LinkedIn. So if you missed the beginning, you don't have to worry. And really sorry for the technical issue in the beginning.
Okay, then if there is not further question.
If you have any question later, you can ask it in our LinkedIn site, in the event chat, or just grab a message to us, and we will, of course, answer the questions.
And I would say again, we can share with you these complex scenarios videos. Unfortunately, I couldn't show for you. If you don't mind, I'll stop the video camera.
I see one more question. Are these test scenarios useful for the autonomous driving system? In my opinion, ADAS or level 2/3 is still obviously different from the autonomous driving.
Yes, my opinion is that we have to go step by step. So the autonomous driving is much will become or will appear, I think, in the next maybe 20 or 30 years, but I don't know exactly. It's my opinion, but we have to cover all of these needs coming from this level 2 or level 3 ADAS systems. And if we start to combine this type of scenarios step by step, so if we just put more ADAS function into one complex scenarios, we can somehow approach this complex challenges what we will expected in the future. So we have to start it somehow. As I understood well the question, but I don't see this question exactly.
Okay, thank you very much, Márton. And thank you very much for attending to this webinar. We are planning other webinars. If you have any suggestion for the topic, it's very welcome. And yes, we hope you enjoyed. And we hope we will meet again virtually. Thank you very much.
Thank you.